You have a normal office network. PCs are downloading files, cameras are uploading video, cloud apps are syncing, and someone starts a voice call. The link gets busy. The file download just slows down. The voice call breaks up immediately. That is the whole reason quality of service exists, not to create more bandwidth, but to decide which traffic gets better treatment when there is not enough bandwidth for everything. Before QoS policies can help voice, the phone has to fit into the access layer cleanly. An IP phone is not just a handset. It includes a tiny internal switch. The wall jack connects to the phone, the PC connects to the phone, and both devices share one switch port. The switch port still acts like an access port, but with a special exception. Data traffic stays untagged in the access VLAN, while voice traffic rides a tagged voice VLAN. That separation makes voice easy to identify and prioritize. Power over Ethernet solves the second desk problem, power. The switch is the power sourcing equipment, or PSE. The phone, access point, or camera is the powered device, or PD. A PoE switch does not blast power blindly. It detects whether the device supports PoE, classifies how much power it needs, starts it up, then monitors normal operation. Show power inline, verifies power budget and connected devices. Power inline auto is the normal default. Static reserves power, never disables it. Power policing can shut a port down if a device draws too much. Now QoS begins with symptoms: delay, jitter, and loss. Delay is one-way travel time. Cheerthing in seconds or less. CCNA recommends voice delay stay at 150 milliseconds or less. Jitter is variation in delay. Voice should stay around 30 milliseconds or less. Loss is missing packets. Voice should stay near 1% or less. TCP apps can retransmit lost data. Voice usually uses UDP, so retransmission would arrive too late. Too much delay, jitter, or loss means choppy audio. A device must classify traffic before it can prioritize it. Classification means deciding what class a packet belongs to: real-time, business-critical, default, or scavenger. That can be done with ACLs, ports, or deeper inspection such as NBAR. But doing complex classification on every hop is wasteful, so packets are usually marked early. Later devices can simply read the mark instead of re-inspecting the whole flow. There are two major QoS marking places to remember. PCP, also called QoS, is a 3-bit field in the 802.1q tag. Voice commonly uses PCP5, but PCP only exists while the frame is tagged. So DSCP is different. It is a 6-bit field in the IP header, so it can travel end-to-end. Default forwarding is best effort, value 0. Expedited forwarding, or EF, is used for delay-sensitive voice, value 46. Class selector keeps backward compatibility with IP precedence. Assured forwarding uses class and drop precedence, like AF41 versus AF43. Markings are only useful if you know whom to trust. That is the trust boundary. IP phones are commonly trusted because they mark voice correctly. PCs usually are not trusted because a user could mark a giant file transfer as EF and steal priority. The switch or phone should remark untrusted PC traffic according to policy. Trust the phone. Verify or rewrite the PC. When an interface receives packets faster than it can transmit them, packets wait in queues. Without QoS, One FIFO queue sends packets in arrival order. Priority queuing sends high-priority queues first, but can starve lower queues. CBWFQ improves fairness with weighted round-robin and guaranteed bandwidth per class. LLQ combines both. Voice gets a strict priority queue, while other classes use CBWFQ. T-Drate. But the priority queue needs a limit, or it can starve everything else. Policing and shaping are rate limit tools, but they behave differently. Policing drops, or sometimes remarks, traffic that exceeds the configured rate. Shaping buffers excess traffic and sends it later at a smoother rate. A common WAN example is a customer with a gigabit physical link but a 300 megabit service contract. The ISP polices at 300 megabits, so the customer shapes outbound traffic to 300 megabits to avoid unnecessary drops. Finally, congestion avoidance deals with queues before they overflow. Tail drop waits until a queue is full, then drops everything new. That can make many TCP flows slow down together, then speed up together, creating global synchronization. WRED starts dropping some TCP packets early. WRED does the same thing with awareness of markings and drop precedence. Do not use WRED or WRED for voice priority queues. Voice does not handle loss well. The exam phrase that ties all of this together is per-hop behavior. QoS is not magic carried by one marking alone. Each device must be configured to treat markings consistently. Classify, mark, queue, schedule, police, shape, or drop according to policy. Remember the story. Separate voice with the voice VLAN. Power the device with PoE. Mark important traffic with DSCP. Trust the right edge. Then, use queues and rate controls so voice survives congestion.